Hi guys. So the other day I had to write up a little example program to submit as a bug report for a Fortran compiler that I won't name right now. Uh, but the example I put together seemed like a really good way to demonstrate a technique that I use pretty frequently in library and other code that I write for Fortran. So I want to just kind of give you guys a tour through it and kind of walk through how it works and discuss the basic principle behind it. The idea is recursive data structures in Fortran. So let's jump over and we'll take a look at the code and then we'll kind of walk through an example of what's going on under the hood and how this stuff works. So let's start off here with the main program really quick just to kind of get it out of the way. This is a really simple just like kind of driver program just that allows us to interactively ask for which Fibonacci number are we going to want. And so the basic idea here is we're going to use a recursive algorithm for calculating Fibonacci numbers, but we've added some additional complexity in the middle here that builds up a recursive data structure that then is then going to actually do the calculation. So we've kind of split it up into two parts. And so this main program is just so that we can ask the user at runtime, how many Fibonacci numbers are we going to calculate here? And then we're gonna use the entry point into our little library here that's gonna generate that recursive data structure, and we're gonna save it in this variable, and then we're gonna use that recursive data structure to actually do the calculation to calculate the Fibonacci number that we've asked for. So now we can start taking a look over here at the library itself. So the way we generally implement these recursive data structures is we'll have an abstract type and then two or possibly more types that extend from that abstract type. In other languages, this would be like base class and child class, but in Fortran, they're just called types. So we'll have this abstract type that kind of defines the interface to this kind of recursive data structure. What are the kinds of things we're going to be able to do with it? In this instance, we're just going to want a single calculate procedure that's going to calculate the Fibonacci number for us. And so what we'll do, so we have to define the interface to that procedure. It's going to be a function. It's going to take the object itself, and so it's going to be class Fibonacci abstract, so that's that abstract type. Takes that as an input, and it's going to give us back an integer that is the Fibonacci number. And so then we're going to have two or more types that extend from that, one of which is going to be kind of its own standalone thing in this case. So we've got Fibonacci base t, and it has to override that deferred procedure. So we specified the interface to this procedure here, but not an implementation, so we call it deferred. And so in Fortran, a type that extends from an abstract type that has deferred procedures has to define implementations for those procedures with matching interfaces, or it has to be abstract itself. And so we don't want this type to be abstract. We want to define a procedure for this. So we've got the procedure base calculate, and it has to be called with the same name. And then and this isn't going to have any components because we're not going to need any. This is kind of the bottom level of this recursive data structure. Like this is the end point. In recursive data structures, generally you'll have kind of a tree structure. And so the leaves of the tree will be this base type here. And then the other type that extends from the abstract type we'll call Fibonacci recursive. And it's going to have components, in this case 2, but it could be many, it could be 1, depends on the data structure you're trying to create. In this case, we're going to have 2 components, and they're going to be of class Fibonacci abstract, and they're allocatable. What that means is an object of this type can hold on to 2 objects that extend from Fibonacci abstract. So it could hold on to 2 Fibonacci recursive objects, or it could hold on to 2 Fibonacci base types, or one of one and one of the other, right? But it won't know ahead. It doesn't know ahead of time which type it's going to actually hold on, which actual type it's going to hold on to. It's just going to be one of these, and so we use this class here. And of course, for this one, we also have to provide an implementation for the calculate function that's deferred in the abstract type. And so what are the implementations for these recursive functions? So for the base type, we're going to say that the Fibonacci number is 1. Right? So this is kind of like the base case in the recursive Fibonacci implementation, right? A recursive Fibonacci implementation is just the Fibonacci number is the sum of the 2 previous Fibonacci numbers. So generally it's if n is less than 2, then Fibonacci number equals 1. Less than or equal to, then Fibonacci is 1. Otherwise, it's the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So this base case is basically going to be, the answer was 1. So we don't need to we don't even need to look at the input value here because it doesn't have any components. And so this trick, associate unused to self. This is just a trick so that the compiler doesn't warn you that you didn't use your argument. So the result of that function is just going to be 1. For the recursive calculation case, now is when we use the 2 types that we're holding on to. So the Fibonacci number from the recursive branch, note that we need to mark this function recursive. It may not call itself directly, but it's potentially calling itself indirectly, right? So this is class Fibonacci abstract, so we don't know its actual type. So it might actually be calling itself. And so it's a recursive function, and so we need that recursive keyword there. But so the Fibonacci number from a recursive type is the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number, right? And so that's the basic algorithm that we're using, is that just general recursive algorithm for calculating Fibonacci numbers. We've just built up this data structure to do the calculation. So how do we build up that data structure? It's pretty much identical to the recursive Fibonacci implementation. It's just instead of doing the calculation when we're doing the recursion, we're building up this data structure. So if the Fibonacci number we've asked for is 2 or less, then the type that we return, we'll back up for a second. The generate Fibonacci calculator, which is the function that we called from the main program, is building up this data structure. So its return type is class Fibonacci abstract. So it might return a base, or it might return a recursive. So it's going to return a class Fibonacci abstract, and it has to be allocatable. And so we're returning a calculator, which is this recursive data structure. So if we've asked for the nth number 2 or less, then we're going to return just a base type. And so this is the structure constructor that you kind of get for free for derived types. Since it doesn't have any components, it doesn't take any arguments. If we're asking for if the Fibonacci number we're asking for is more than 2, then we're going to create the recursive type where its two components are generate Fibonacci calculator with the nth number minus 1 and the nth number minus 2. So we're calling this procedure recursively. So this might return a base type, or it might return another recursive, right? So this is how we're building up this recursive data structure, is via a recursive algorithm. So basically we're using recursion in 2 stages here. We're using recursion to build up a recursive data structure, and then we're using recursion to walk through that data structure to perform some calculation. And that's the basic pattern or principle that I actually use quite frequently in a lot of the libraries and code that I write. It often gets a lot more complicated. Generally, the where you'll see this done is these recursive functions that you're going to call through the recursive data structure. They take some other argument that isn't available at the time that you construct the data structure. Right? So you'll construct this data structure based on some available data, and then later you'll pass some arguments down through that data structure to do some calculation. So in this instance, we could have just done the calculation directly. We didn't need this recursive data structure, but it's a simple example that allows us to demonstrate the basic pattern. But once you have this basic pattern, there are more complexities that you can add to solve some complex problems that involve situations where the problem forms itself kind of naturally into this recursive algorithm. So we can give a quick demonstration for how this works. I've made this open source as an FPM package. So we'll just use FPM run, and it's going to ask me what number would I like. So let's do the 6th Fibonacci number, and that 6th Fibonacci number is 8. 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 2 is 5. And 5 plus 3 is 8. Right? So that's how we get to the 6th Fibonacci number, is being 8. So now we'll work through how this calculation actually gets performed, how it builds up the recursive data structure, and then how it performs that calculation to get us to the 6th Fibonacci number using that recursive data structure and then the recursive algorithm. I'm just going to hop over to a blackboard so we can draw this out. But let's kind of work through this example, and this will help you kind of get a more concrete understanding of how this plays out in runtime, at runtime, how this stuff works.
So for reference, I've written up here in kind of pseudocode the basic procedures that we're going to need here. So generating the data structure and then doing the calculations based on it, just for reference while we go through this. So the basic idea is we want to calculate the 6th Fibonacci number using this recursive algorithm, building up a data structure and then traverse forms on calculation. So we'll start with, we want to calculate the 6th Fibonacci number. And so where we're going to start is we call the gen fib calc to generate this recursive data structure. So we're calling it first with 6. And so if the argument is 6, so it's not less than 2. So we're going to generate a recursive object. But it needs 2. And so to denote the recursive object here, I'm going to use a circle, and we're going to have 2 branches. And I'm going to leave this little annotation here so we kind of know where we are. So we need gen fib calc with n minus 1th. So we need 1 for 5 here, and I'm going to draw these way over here to the sides. because we're going to need lots of room. So for the fifth, so we'll start over here. So for the fifth, we need 5 is not less than or equal to 2. So we need another recursive with n minus 1. So n minus 1 is going to be 4. And I haven't spaced myself out quite right, so we're going to start to run out of room a little bit here, but we'll deal with that. So 4 is still not less than or equal to 2, so we need another recursive one, and with n minus 1 is 3 over here. So with 3 is still not less than or equal to 2, so we're going to the recursive side again, and this time with 2. So now we have less than or equal to 2, so that's the base case, which I'm going to draw a square for the base case here. So now we can come back up here, and 3 with n minus 2 for the other side, for the other branch, that's 1. But we get another square here because we'll get the base case again, because then n is less than or equal to 2. So now we get 2 of the base cases. So now we need to come back up over here to 4 for the other side. Is n minus 2, so 2, we get the base case again. And you can see we're going to end up doing this several times, and so this tree kind of is slightly unbalanced, but you can see it's definitely a tree structure. So on this side, we're with 3, we already kind of know, but in reality at runtime, it actually is going to build up these like duplicate sections of the tree. So 3 we already know is going to look like this here. So without going through it again in so much detail, I'm just going to redraw it. Right? And so similarly over here, this one's going to be 4, and we've already got that tree over here for 4, so I can just redraw it again. So there we go. That's what so that's what the recursive data structure is going to look like once we've generated in memory. And so all we've done at this point, these numbers were here just to keep track of what was the argument to this procedure. At this point, I'm going to remove them because they're not actually stored in the data structure. This was just to help us keep track of where we were going through this algorithm to build up the data structure. So at this point, the only thing that this data structure has is just this information. We know what the type is at each node, so we know whether it's a node or a leaf, but we don't have any other information. We've just built up this data structure. So next we go through and we call that calc procedure starting up here at the top. So we're holding on to the head of this tree, the root of this tree. And so having built up this data structure, now we call that %calc procedure to say, well, now actually calculate the Fibonacci number for me. So now here's where we start based on the node type, whether it's the recursive type or the base type. Now we know which of these procedures actually gets called as we kind of walk down through this tree. And so for the recursive type, so at this point we're going to call self %first calc. Okay, so now we need to calculate here. So to calculate that one, we get back in the recursive spot again, and again, and again, until we get down to here. So now we know the answer for first is 1 at this node, second is 1 at this node, and so it adds them together, and so we get 2 here. And now we need to come back down the other side for this. So we get a 1 there, and so now we add them together, and so we get 3 here. And now we need to walk down this branch. So we walk down again, we get a 1 here, and a 1 here, so we get a 2 there. And now we're able to add those together, so we get 5 here. Now we need to walk down this side. And so we walk back down to the end of the nodes. And it's actually going to be walking kind of down in this pattern, where it goes down the left-hand side as much as it can, then the right-hand side, then the right-hand side, then the right-hand side, go down left first, then right. So it's walking down and then slowly to the right as it performs this calculation, because it's going to end up performing the first calculation first, then it has to perform the second, and then it can do the addition. And so we get 1 here, which we're able to add together to get 2. Walk back down the other side, we get a 1 there. Add those together, we get a 3. Now we can do the final addition to get the 8. The answer to the question that we asked, what's the 6th Fibonacci number? It's 8. And so that's the basic way that this is built up, this data structure recursively, then walking through the data structure recursively to perform some calculation and getting a final answer at the end. So that's how this all works under the hood.
So now that we've worked through that example and I showed you the code, you should hopefully have a much better understanding of how recursive data structures work, recursive data structures and recursive algorithms, how they work, and how you could make use of that in Fortran. So if you liked the video, make sure you hit the thumbs up button down there and give it a like. Hit the subscribe button and the little bell icon to get notifications when I release new videos. And let me know down there in the comments if there are some other videos you'd like me to make demonstrating some other principles and or patterns and how you can implement them in Fortran. I will leave a link to the repository that I showed you so you guys can get a copy of the code and play with it. You know, stick print statements in there while it's executing. See if there's anything else you want to do to play with it. Just have fun.